Swayam Prabha. Digital India. Educated India.
My presentation will be in these four parts: the background about process monitoring, an introduction to batch process modeling and the proposed deep learning methods, a case study on the latest industrial scale penicillin fermentation process, and the conclusion. The first part is the background. The Internet is also known as the International network. It refers to the huge network that is connected between networks. These networks are connected by a set of common protocols to form a single logical huge international network. The new generation of information and communication technology is deeply integrated with the industrial economy, and a brand new manufacturing and service system is formed, which is characterized as network, digital, and intelligent. The fourth industrial revolution is an integration of information in time and space to give power, wisdom, and value to smart manufacturing. According to the statistical data as shown in the figure on my right-hand side, most chemical accidents occur in the operation process. With the increasing scale and complexity of chemical industry, the real-time monitoring of the operating status of the production process is becoming more and more important because these faults will not only affect the product quality but also pose threats to human life. In actual production, process monitoring is achieved by the operator's observation of a small number of key variables based on the large threshold is still the mainstream way. This does not consider the correlation among process variables, nor can the large amount of historical data can be utilized. So it is difficult to obtain a promising process monitoring performance. To address this issue, data-driven process monitoring methods have been rapidly developed. The pressure of data-driven process monitoring consists of the following four steps: the way of data collection and data pre-processing is rarely fixed, and the monitoring statistic is a measurement of the change or distance in the feature space obtained by feature extraction. So feature extraction is the key step to define the process monitoring performance. At the core of the development process monitoring method, the development of feature extraction method has been the most intensive and in the past research topic. The principle behind analysis and partial lattice squares can be regarded as the earliest application of multivariate process monitoring. The past 30 years witnessed the rapid development of the driven process monitoring, among which two benchmark processes, one is anti-Eastman process and the other is the PASIC, have been developed for continuous process monitoring and batch process monitoring. This work is motivated by the emergence of ND-PASIC, a benchmark process for industrial scale batch process monitoring, and the web application of deep learning-based process monitoring method. The original concept is to easy with a small scale. The difference between data with different initial conditions is not significant. Independent is developed to deal with this issue by extending it to an industrial scale. and a big dataset with 100 batches is provided here. This work aims to address the following three problems in batch process modeling. The first one is to avoid difficulties caused by data falling for processing in traditional methods. This is benefited from the special batch operation of deep learning models, which will be introduced later. The next one is to monitor industrial scale batch processes with different initial conditions. In industrial batch production, the date and the loss of batch can be significantly different among batches, but the internal reaction mechanism should be consistent. Therefore, this could be achieved by extracting the common date features of different historical batches. The last one is the extraction of within batch non-stationary features of multi-phase batch processes. Traditional recurrent neural networks tend to memory the long-term stationary information, while batch processes are multi-phase processes with short-term non-stationary information. This work proposed a differential recurrent neural network to handle this problem. Next, I will introduce the proposed method for batch process modeling. As we all know, data volume is the most common data processing procedure in batch process modeling because data collected is three-dimensional with an additional dimension of batch. As shown in the figure on the right-hand side, batch size and variable size are two kinds of ways of data volume. However, no matter which kind of way of data volume is implied, difficulties will be brought to affect the further feature extraction. For batch-wise data volume, all batches are required to be processed to equal loss, which means the data supplement must be performed. It will change the internal data information. Moreover, in this way of data volume, data of a whole batch should be given to a return process monitor results. It is not applicable to real-time process monitoring. And for variable data volume, the within batch data features cannot be made fully use of, and the end of the batch is directly connected to the beginning of the next batch, which is not consistent with the true distribution of batch data. Comparatively, deep learning methods can be utilized to handle this issue for their special batch operation. In this work, a moving window with a fixed loss time step is required to input data, as shown in the figure on the right. Once it moves to the end of a batch, it will move from the beginning of the next batch. In this way, historical batches with different initial conditions are input to the deep learning model, and the model is automatically trained to extract useful features from data for better prediction on the quality indicator variable, which can be called as QIV. Batch processes show the following special characteristics: different initial conditions and loss of batch, and within batch multiple features. The first one can be handled by the batch operation of the training model mentioned before, but the within batch multiple features are mostly not focused by common deep learning models. Therefore, a differential recurrent neural network is proposed to handle this issue, in which a differential model is embedded into long short-term memory neural network to make the memory cell capture more short-term non-stationary information. Calculation can be described by the following three parts. The first part is used to model the non-stationary information in the hidden state of the first long short-term memory layer, and the next part is employed to define the amount of non-stationary information that should be returned. The last part is another non-short-term memory structure used to get the final output of the proposed differential recurrent neural network model, comprising the hidden features extracted for QIV prediction. The procedure of the proposed Quality prediction and monitoring framework can be shown in this figure, as mentioned before. Data and volume processing in traditional measures can be avoided by batch operation of deep learning model. The within batch model students can be tracking and produce differential recurrent model, and fault can be detected by monitoring the prediction review of the QI. In the next section, a case study on industrial scale penicillin fermentation process will be investigated to verify the proposed method. Industrial penicillin is an industrial scale penicillin fermentation simulation process developed by Goodrich. Compared to traditional penicillin benchmark, the penicillin simulation in industrial penicillin is extended to an industrial scale and is validated through available real historical data of an real penicillin fermentation process. The data of the bioreactor used in industrial penicillin is shown in this figure. The data can be generated by simulation using mathematics of the lab, and a separate data containing 100 batches of simulation is also provided. This dataset can be regarded as the biggest dataset available for data analytics in industrial batch processes. In this case study, the 100 batch dataset is employed. All these batches are simulated with different digital computers, and the loss of this 100 batch simulation dataset ranges from 167 hours to 190 hours. Batch information in the process level with a sampling frequency of 0.2 hours used in this work are shown in the table. The first 22 variables are used as the input variables, and the penicillin concentration is selected as the parameter because it is the hidden feature of the dichotomy. Variable selection is first performed in our proposed successor modeling framework. Generally, the variable selection is implemented through selecting meta variables that show significant correlation with QIV. Considering that the industrial batch processes are significant nonlinear processes, model information is used in this work to calculate correlation between input variables and QIV. To obtain a threshold for model information, a thousand pair of normally distributed sequences are randomly generated, and the model information between each pair of sequences are calculated. The model information values should be distributed around a small value because these sequences are independent and the correlation between them is mostly contributed by random factors. The threshold and the 9% confidence level can be defined as 0.055 by kernel density estimation, about which the correlation between this variable and the QLA is considered significant. According to the result, two variables are solved. The proposed method is compared with partial least squares regression (PLSR), support vector regression (SVR), neural network (ANN), recurrent neural network (RNN), and long-short-term memory neural network (LSTM). Regarding the parameter selection of different methods, the number of principal components in PLSR is selected as 14. The model parameters C and gamma of SVR are selected as 2 and 0.005. The structure of all deep learning methods is chosen to be a three-layer network with a maximum of 128 edge nodes, and the optimizer is Adam. The learning rate is selected at 0.0001 to ensure the model could convert to a satisfactory state. The other two verify that the performance improvement is contributed by the model structure design. A similar number of parameters are designed for all deep learning models. and the sequence loss is determined by the grain searching as shown in the figure because it is a more important parameter to the model performance. Actual value and estimated value of penicillin concentration in test batches are shown in the figure. Solely based on the observation of this figure, POSR doesn't perform very well because it is not used to handle nonlinear and dynamic features. The prediction error of ANN is also large. The reason could be the poor generalization ability of the model. And SVR performs better than the Bob-2 model because of its powerful fitting ability to nonlinear processes. However, the training time of the SVR model is much longer than all other models for large data sets. RNN performs better because the sequence information has been considered through the transition of hidden space. LSTM further outperforms RNN due to its ability to handle long-term time dependency. As for the proposed DRN model, prediction accuracy is further improved because the within batch local information of multi-phase batch processes could be captured by the proposed method. In order to quantitatively compare the prediction accuracy of this method, all the 6 evaluation indicators are calculated for test batches according to the table. The proposed DRN model shows the best performance on all the 6 indicators, which means that not only high fitting accuracy can be obtained, but the distribution of estimated values is the closest to the actual distribution. As mentioned before, the prediction residues are employed as a statistic for quality monitoring, and a threshold is defined according to the residues calculated using data under normal operating conditions. All 60 test batches are under normal operating conditions, and 2 test batches containing faults are used to verify the performance of quality monitoring. According to the results, the model achieves a high prediction accuracy for QLV in normal batch, and the cycle false alarm rate can be returned. And high false alarm rate is mostly caused by the failed batch, in which alarms should be triggered to early terminate the production. Overall, failed batches and faults can be effectively detected by the proposed measure. For the last part, I would like to make a conclusion. A quality-related industrial scale batch process monitoring rate based soft sensor development is presented. The use of deep models avoids the limitation caused by batch processing and embedding differential operation into long-term memory network can improve soft sensor prediction performance. The method is verified by an industrial scale continuous formation simulation process. Results observed by proposed framework demonstrate its potential industrial application prospects for multi-phase batch process operations. And future research associated to batch process control can be conducted based on the proposed framework. That's all for my presentation. Thank you very much for your attention. If you are interested in our views EPS, welcome to contact Professor Richard and questions or concerns regarding the work. Please don't hesitate to contact me.
Okay,